All right. This is oh nope, that's the next section. Sorry, this is the section that we're doing, the fifth part. Um, Calculating forces in an electric field in two dimensions. This is what we're gonna do, and this actually leads into the next section. So I wasn't entirely wrong there, right? Okay. In the diagram shown to the right, two equal charges, positive q, are placed on the y-axis at distances a on opposite sides of the origin. Point P is the location on the x-axis at x equals x naught. Okay, great. Determine the magnitude and direction of the electric field at point P in terms of q, a, x naught, and k. All right. So really quickly, something important to note here is that when you have these two charges here, okay, and when they apply their field on P, you're going to notice that you're going to have a bunch of, there's vertical components to those fields as well, but those vertical components cancel out, so it doesn't even really matter, right? So you'll notice that the field that is applied by Q is going to go up this way, okay? Or sorry, it's applied by the lower charge is that, and then this one is going to go this way. Okay, and the vertical components of those two are going to end up canceling each other out. So you're just going to be left with a net horizontal charge going straight to the right. Okay. Okay. So let's take a look. Okay. If I figure out, okay, if I know that the electric field is equal to kq over r squared, okay, and I know that really the net electric field is going to be equal to the x component of the top charge electric field plus the x component of the bottom charge electric field. Okay. Then what I'm going to have to do is I just need to add those two up. I need to figure out what the x component is of that. Okay. I will need to use theta. Okay. Right there. Now, these two charges are equal in magnitude and they're equal distances. So really, this is just can be written as 2 e sub x. Okay, so if I can figure out the x component of one of the charges, one of the fields from one of the charges, then I can figure out, then that's the same for both of them. I just multiply by 2. Okay, so in order to do that, I need the adjacent side, the side adjacent to the angle, and that's going to be cosine. So I'm going to use um, E net is equal to 2 e cosine theta. Okay? And we already know that e is equal to kq over r squared, so this is just going to be 2kq over r squared cosine theta. Okay? And I can actually replace cosine theta because if I know that cosine of theta is equal to adjacent over hypotenuse, right? The hypotenuse is going to be, I'm going to call this the distance r, which is going to be root x naught a squared. So x naught squared plus a squared is going to be my hypotenuse. Okay. And then the adjacent side is the distance right here, which is just x naught. Okay. So I can actually replace cosine with x naught over root x naught squared plus a squared. Okay. And that would be perfectly fine because they're equivalent. Okay, that's a trig identity. X naught over so x naught over I'm just gonna call this r. Okay, I've already called it r. I don't want to write the whole thing, so I'm just gonna call it r, right? And that's gonna be the same as this r right here. Okay. What I can do now is I can just multiply it together. And so I would end up getting that the net electric field is equal to 2kqx naught over r cubed. You can write it like that. That's fine too. I'm going to expand it out because I'm going to use it a little bit later. 2kqx naught over x naught squared plus a squared to the 3/2 power. Okay, those are equivalent expressions. You can say either one. I'm just expanding it because I am going to use that a little bit later. Okay. At sufficiently large distances from the origin, the electric field can be we can approximate this as a point charge, as a singular point charge. Okay. Because we can make a couple of using some approximations here. We can say that if x naught is much, much greater than a, okay, then I can say that x naught squared plus a squared is equal to just x naught squared, because the x naught term would be so overpowering that it would it would basically render the a completely irrelevant. Okay. Okay. So in that case, what I could do is I could then say that let's see, the E field is about 2kqx naught over, this term is just going to be, again, we've already said that this right here is just going to be equal to x naught squared to the 3/2 power. Okay. And that will actually cancel out. The exponents here, the 2 and the 2's and the exponents are going to cancel each other out. And then we end up getting that this is going to be 2kqx naught over x naught cubed. And then you should notice that your x naughts will cancel out. Okay? So you end up with 2 in the denominator, which is exactly what we're looking for right here, is 2kq over x naught squared. Now, here's the thing, okay? I do need to prove that this is, I do need to prove to you that this is actually the same form as that, okay? The first thing is, the two major things here is this, okay? If I've said that x naught squared plus a squared is equal to x naught squared, then the square root of x naught squared is just x naught, right? So that means that r is equal to, that whole root x naught squared plus a squared thing, right? Well, then this would just become root x naught squared, which is just x naught, okay? So I can replace x naught with r, and this is still valid, okay? I can also say that the net charge, well, you've got one q and another q, so that's just 2q. So I can turn this 2q into just q net, and that gives me the exact equation that we were looking for. So this is perfectly fine. This approximation checks out because of these two major things that we have to consider. Okay? Okay. Now, consider the same situation, but the bottom chart is replaced with negative q. This one is a little bit different. Okay, it's slightly different because now instead what you're going to see is that the top charge is still going to do the same thing that it did last time, but the bottom charge now, instead of repulsing it, it's now going to pull it. So then you end up having the horizontal components cancel out, and this looks a little bit different. Okay, and so we could see that the net field, instead of it being the sine component, it's going to be 2e sub y, which is going to require us to use which will require, so instead of using cosine, we're now going to use sine. Okay, so it's going to be 2e sine theta. Okay, and then I can then piece this together. Okay, E net equals 2kq over r lowercase r. I'm trying to be consistent with my symbols here. This should be lowercase r squared. Sine is going to turn into, we know that sine theta is equal to opposite over hypotenuse, right? So we can turn this into, the opposite is going to be a now. So this is going to be a over the hypotenuse, which is still going to be r. Okay, so that really just gives us 2kq a over r cubed. It looks very similar to how it did last time. The only major difference is that now instead of having x naught in the numerator, we have a in the numerator. Okay, so this really is just going to become 2kqa over x naught squared plus a squared to the 3/2 power. Okay, boom, beautiful. Okay. Okay. Something is I guess my group chat is like blowing up right now, but it's okay because I'm on the last problem, so I can respond to them soon. I wonder if they want to hang out. There's now this approximation does not work for this case. Okay, it worked for the previous case, but it doesn't work for this case, and there's two major reasons why. The first one is that the first one is that first off, Q net is equal to 0. Okay, so E equals K Q net over R squared would be equal to 0 as well. So the approximation means nothing to us. Okay, we know for a fact that there is E field at the point. However, this is telling us a 0. It means nothing to us. It doesn't tell us anything. The other thing is that if x naught is greater than a, okay, you get an inverse cube relationship. Okay? You get an inverse cube relationship, and it should be inverse square. Okay? And you can solve that out. I'm not going to, I can kind of walk you through it a little bit. This ends up being x, this would end up being, actually it would be the exact same derivation as above, except we would actually not be able to do this last step right here. So you would have this result right here, and it would end up being x naught cubed. That's an inverse cube relationship, and there should actually be an inverse square relationship between electric field and distance. Okay? Okay, that is that part right there. All right, live, laugh, love, have fun.